Hello, I'm Luca Bertaccini. I am with the Pulp team at ETH Zürich, and I'm excited to present today MiniFloat-NN, our RISC-V ISA extension for low precision NN training. In the past few years, the memory and compute requirements of NN model have been growing very rapidly. We witnessed 3 orders of magnitudes in only 2 years. And in this context, hardware architecture is facing quite some challenges since we need to provide efficient support to train these kind of networks. In this context, technology scaling is not sufficient, and we do require algorithmic and architectural advancements. From the algorithmic side, new, more compact, low-precision data types have been recently proposed. There's been a shift towards lower precision formats, passing from the 32-bit float down to 16-bit or even 8-bit floating point data types. All this helped lowering the memory footprint of NN models. It opened for very interesting opportunities to improve the efficiency of our hardware architectures, and generated quite some interest around these new formats and operations that can leverage these new data types. In the RISC-V community, we have the new FP SIG. We also have the IEEE P3109 that is actually looking into standardizing these new formats. However, when we go to such low precision formats, we have a few number of bits that we can use. So most of the time you would like to employ these kind of formats in a mixed precision algorithm where you perform the accumulation in higher precision. So in this kind of context, you would use what we call expanding operations that starts working on lower precision inputs and accumulating higher precision. As regards the architectural advancements, what we could do to improve the efficiency of our architecture is making the design domain specific. We could go directly to very specialized hardware accelerators. But if we proceed this way, we would also narrow down the application scenarios in which our architecture would represent an attractive solution. But here is where RISC-V come to help us. With RISC-V, we can enhance general purpose CPU with domain-specific ISA extensions. And in this way, we will be able to deeply optimize the processing elements of our systems without compromising the baseline standardized ISA. So we will not narrow down the application scenario in which that we target, but we can be much more efficient in some specific scenarios. And this is what we tried to do with our MiniFloat-NN. This is a nice extension for low precision NN training. So we have tried to, we have worked toward extending an HPC RISC-V system to have efficient support for low precision training. We have started by looking at efficient clusters that can be hierarchically replicated to build HPC RISC-V systems. And then we look at a set of instructional formats that would have helped us enabling low precision NN training on the RISC-V architecture. And finally, we implemented an hardware unit capable of carrying out such instructions. So our starting point is manycore. This is a chiplet-based hierarchically scalable architecture. It contains a Linux-capable host that is enhanced with a large manycore accelerator built upon the replication of efficient L1 shared compute clusters. Such clusters are the snitch clusters. They contain area-optimized, scalar, very small 32-bit RISC-V cores, coupled with large FPUs that have support for single and double precision, and also SIMD capabilities. All the cores share a scratchpad memory and are enhanced with ISA extensions that implicitly encode the loads and store to register reads and write, and are able to map loops in hardware. So all this combined allows us to reach around 90% of FPU utilization. And what we are missing is actually the support for low precision formats and expanding instructions. So we have been looking into that, into which kind of formats and instruction would have been the best target to extend our ISA. And if we have a look at the baseline scenario where we have our scalar core with no mixed precision capabilities, and we want to port one of these mixed precision kernels into our architecture, well, we have a problem because we don't have the instruction that can handle mixed precision. So what we would have to do is either to convert our input on the fly, which would affect our performance, or we could directly size our kernel to use the higher precision needed for the accumulation. And if we proceed this way, we consider a kernel that has FP16 or bfloat input and accumulate in FP32. Same odds for kernels that start from 8-bit inputs and accumulate in FP16. In this case, if we consider FP32 accumulation, we would be able to map 2 of them in a SIMD way. But if we had support for mixed precision instructions, we would be able to exploit the lower precision inputs and therefore mapping twice the number of elements into our registers, keeping the same bit width for the accumulator. So now we have to process all the data that we have inserted in our registers, and to do that, we need to do twice the work that we were doing before. We can do that by using an expanding sum of the product that does the 2 multiplications and 2 additions. It reuses the same higher precision accumulator but processes now twice the number of input elements. So we reach twice the performance that we were able to reach with the FP32 SIMD, or we can think about reaching the same performance of an SIMD FP16 kernel, but in this case we can take advantage of the higher precision accumulator. Finally, we can find ourselves in the situation in which we need to reduce the results that we have packed in the registers with the accumulator, and we introduced a 3-term addition instructions to be able to do that rapidly. As we will show later, this has been mapped on exactly the same hardware, so it basically came at no hardware overhead. But expanding some of the product also offers further benefits. We are fusing 2 FMA into a single unit, so we can have a single normalization and rounding step. We can take, we have the opportunity also to mitigate some of the issues that might arise by having the 2 non-consecutive floating point additions in the same, inside the same hardware unit. We have then looked into the floating point formats that our unit would have supported. We are targeting low and mixed precision training, so we selected 2 FP16 and 2 FP8 formats as for our inputs. And as destination formats, so basically the format of our accumulator, we selected twice as many bits. So if we started from 8-bit inputs, we would accumulate in 16-bit. And if we started from 16-bit input, then we would have accumulated in 32 bits. So we have quite a wide set of formats. We are actually looking into mixed precision instructions. So summing up the 2 things together might result in a large number of instructions that we want to add to our RSA. And to avoid that, we decided to map the alternate format to FCSRs. So basically, we will have a single instruction that says we want to do an expanding sum of the product from 8 to 16-bit, and then whether our input will be in one or the other of the FP8 format that we support will be decided upon the status of the FCSR. Okay, so we have found a cluster that we wanted to extend. We have now a set of instruction and formats that we want to support on our unit. We are missing another functional unit that is actually capable of performing the expanding sum of the product. And we have that open sourced. We developed it and uploaded it to GitHub. This is a parameterized multi-format unit supporting the expanding sum of the product and the 3-term additions we just mentioned before. The unit will do twice the amount of work of an FMA, so we have 2 multiplications and 2 additions. However, merging 2 FMA into a single unit creates also other challenges, mainly due to the 2 consecutive floating point additions. So we addressed that by adding a 3-addend sorting before the 2 consecutive additions and by increasing the internal bit width before each of the others. Finally, when we do low precision NN training, we also would like to avoid stagnation. This happens sometimes in backpropagation when long sum of small quantities are lost to rounding. And to mitigate the kind of issues, we added stochastic rounding. So this was mapped as a new rounding mode. We are still supporting all the RISC-V rounding modes as round to nearest even, but this can be additionally, this is additionally support and can be enabled for this unit. Finally, as we mentioned, we have the 3 added additions. We have all the logic already in our unit, since after the multipliers, the bit width will be increased, and we have everything in the destination precision. So the only thing we needed to do to support the 3 added addition was basically bypassing the 2 products. Okay, so now we have a set of instructions, we have our unit, we have a set of format. We need to extend the snitch cluster with our access.p unit. The snitch cluster contains the CV FPU as a floating point unit. This is a highly parameterized open source modular energy efficient FPU. And we added here our support for some of that product as an operation group block. Since we have an FPU that supports double precision, it has 64-bit inputs, and we are targeting low precision and in training, we can actually have more units in parallel and use them in arranging them in a SIMD unit. So we have 2 16 to 32-bit access.p units and 2 8 to 16-bit access.p units, and we reuse larger precision unit for lower precision computations. So basically, we are able to compute up to 4 8 to 16 access.p per cycle, or 2 16 to 32-bit access.p per cycle. We still added support for this lower precision format to the other operation group block to provide a bit more flexibility in using this kind of more compact data types. And we have implemented our system in 12 nanometers technology. We reach 1.2 gigahertz in a typical corner scenario. And our unit occupies around 45 kilogate. This amounts to around 27% of the enhanced FPU area. And if we also consider the other unit we inserted to handle the low precision formats, everything included amounts to less than 15% of area overhead at a cluster level. So here we are really taking advantage of the low precision of these formats and the low number of bits that we need to handle. But we also have quite some nice opportunities to improve the performance and efficiency. So we have ran some FMA-based gem kernels. As expected, the trend is the lower the precision, the higher the performance, the more data we can fit in our L1 memory, so the larger the gem size that will fit there. If now we pass to an expanding some of the product-based gem, we can basically keep the same performance, but having a larger precision accumulator. And since this is sometimes a requirement, in that case, we would have had to use the FP32 FMA-based gem kernels that we can outperform by 1.9 times. If then we consider the FP8 to FP16 case, this is basically the point in which we reach the highest performance and efficiency point. We can outperform the double precision case by 7.2 times, and the efficiency will be improved by more than 7.5 times. Here we are taking advantage of another slight gain that you can gain by going SIMD at lower precision with respect to having a scalar double precision FMA. All this came at the cost of only 15% of area overhead, and also allowed us to take advantage of the reduced memory footprint. Again, the 7.2 speed up might have also achieved with FMA, but in that case, we would have had the larger accumulation precision. And since we have very few bits, in that case, our kernel might have not been even useful because of the very low precision that we can have there. Finally, we have been looking at vector extension of RISC-V, because there we actually have an instruction that is capable of doing mixed precision operation, which is the widening, multiply, and accumulate. It can take then advantage of the lower memory footprint of such formats, but it underutilizes the FPU bandwidth. So we have a double precision FPU. We will have 3 input. Each of them will be 64 bits. And if we do expanding of MA, 2 of them will utilize only 32 of these 64 bits. So what we could do here is actually provide the FPU with more data and do more computation at the same time, which we can achieve with our expanding sum of the product. We have added our unit to compact vector processor that has been conceived as an alternative building block for the manycore architecture. This is a bit different architecture from the usual RISC-V vector processor that we see. It has coupled to a very small core, and it has a small latch-based vector register file, and allows us to reach around 95% of FPU utilization. Also in this case, the support for expanding some of that product proved to be very useful because we were able to outperform the expanding, fuse, multiply, and accumulation by 1.96 times, since here we are doing basically twice the work every cycle. And we also had an energy efficiency improvement by around 50%. To conclude our talk, our unit is open source, so if you're interested, feel free to check it out. It's on GitHub. I've also inserted a reference to our paper that presented at ARIT that contains a bit more arithmetic details on our unit. And that concludes my presentation for today. Thanks a lot for joining the talk. If you have any questions, I will be happy to answer them. Thank you.